Hey guys, in this short lecture, we're going to talk a little bit more about some basic chemistry, talk a little bit about energy and properties of different types of bonds and things. And at the very end, just mention chemical reactions. So, you've probably heard about potential energy and you've heard of kinetic energy, but what exactly is it? We always like to say potential energy is the energy of position, and it's basically where something is, because where something is determines how much potential energy it has. Think of water. If water is just lying on the ground, it has no energy. But if we put it up high in the air, like behind a dam at a high elevation, we can now let that water run down through a pipe and down through a turbine. And as it's moving, that potential energy, that stored energy of water behind the dam, is going to be turned into kinetic energy as it moves through the pipe and turns a turbine and generates electricity. So in this little short picture right here that we have of these two divers, which one has more potential energy? That's right, you got it. The one on the left, the one that is higher, because when she jumps off that diving board and she hits that water, she's going to hit that water with more velocity. And energy is equal to velocity times mass. And so when she hits it, she's going to be going faster. She's going to have more energy, and so on and so on. In my classroom, I represent energy by E with a circle around it. So if you ever see me draw that on the board, that means energy. And a small lowercase e with a negative sign means electrons. So in this case, molecules represent potential energy. Molecules that have a bond, specifically covalent bonds, represent stored energy. And I always like to tell my students is electrons represent energy. When they're in a bond, in a covalent bond, such as we see here in this water molecule, H2O, they're kind of locked in position. They're moving a little bit, but they're not moving a whole bunch. When we break the bond between hydrogen and water, those electrons are going to be free to move, and that's going to be kinetic energy. They're going to be moving around. Okay, so right now, when they are in a bond, that is a form of potential energy. It's kind of like a battery. A battery is stored energy, potential energy. Think of the bonds, specifically covalent bonds, which result from the sharing of electrons. We'll get into this a little bit more in a second. Okay, so here we see on the left-hand side, we have two hydrogen molecules, and we see that each hydrogen has one valence electron. How many electrons does that inner shell need to be full? It needs only two. Oxygen, as you can see, has 6 valence electrons. How many valence electrons does it need in its second shell in order to be full? It needs 8. So in order to fill both shells, if they share their electrons, the hydrogen and the oxygen, let's look at the right-hand side. And as you can see now, hydrogen now has 2 electrons in its outer shell. Oxygen now has 8 electrons in its outer shell as a result of this sharing. Those shared electrons represents a covalent bond. Kinetic energy is the energy of movement. Here's the diver coming off the board. She's moving through the air. She is showing kinetic energy. Same as with an electron. Those electrons are moving around at the speed of light around that small little nucleus. They're constantly moving in this cloud somewhere. We can't predict where they're going to be. They're moving very, 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 very fast, and that is the energy of movement. Those electrons represent energy. Excuse me. The electrons are going to basically give a molecule its properties. All right, because it's those valence electrons. And what's a valence electron? The valence electrons are the electrons in the outer shell. The number of valence electrons are going to determine how reactive a molecule is. If it has 4 or less valence electrons, or I should say 3 or less valence electrons, the molecule will most likely lose those valence electrons. And if it has 5 or more, it will generally gain electrons. It will steal electrons from something else, okay? Or it will form covalent bonds. It all depends a little bit. If you click on that periodicvideos.com, if you go to that, that's a really cool website that has little videos about every single element out there and some really amazing information and some cool little video clips. Families, on the other hand, run vertically. And what do we know about families? Families are kind of alike in a lot of ways. They look alike, they may act alike, they may sound alike, and that's the same thing in the periodic table of elements. Anything that's in the alkali metal family, all are going to react very similar to each other. Everything that's in the halogen family are all going to react very similar to each other, as are the noble gas, the oxygen, nitrogen, so on and so on. They have the same number of valence electrons. The number of shells they have are different. Remember, in the top one, that's period 1, there will only be 1 shell. In the second row, that's period 2, there will only be 2 shells. But in the families, the number of the outer electrons are going to be the same. So in the alkali metal family, they all have 1 valence electron. In the halogen family, they all have 7 valence electrons. And because of that, they're going to have similar properties. All right, so I said we were going to mention covalent bonds once again. Remember, covalent bonds are when 2 elements or 2 atoms share electrons. Generally, they share electrons so they can fill their valence electron shell. So here we have carbon and 4 hydrogens. Carbon has 4 valence electrons. Its atomic number is 6. That's 2 on the inner, on its inner shell, which is now full, and it has 4 valence electrons in its outer shell. Well, how many does it need again? That's right, 8. And so what it does is it makes bonds with 4 different hydrogens. How many do they have again? That's right, they have 1 each. How many do they need? 2. So by sharing electrons with the carbon, they can both fill their valence electron shell. And we have 2 different representations of a methane molecule. Okay, that's what that is, and some of us produce more of it than others. Those are 2 different representations of a methane molecule. The one on the right-hand side is what we call a structural formula, and you are going to become very well versed in how to distinguish the different types of structural formulas of the 4 major groups of macromolecules. Now, here's water, and we're going to talk about more water a lot more in the next lecture. It is what we call a polar molecule. Why is that so? What's that mean? It means that the electrons are really not shared equally, and oxygen loves electrons. It has a very high electronegativity value, and so therefore, even though they're sharing electrons in their covalent bonds between the oxygen and hydrogen, oxygen really likes those electrons, so they have a tendency to stay closer to the oxygen than they do the hydrogen. And that results in unequal distribution of electrons in this molecule. So more electrons around the oxygen side means it has more negative energy. And less electrons on the hydrogen side means there's a little bit more positive energy on that side. And so even though the molecule is neutral overall, one side slightly positive, the hydrogen side, and one side slightly negative, the oxygen side. And we're going to see how this plays out in life. Okay, as I said, this is a structural formula, again, methane, and it just basically shows the basic shape of the molecule in a 2-dimensional world. Remember, these are 3-dimensional molecules. That's not really what it looks like, but that's how we draw it. It's easy to draw, shows 4 covalent bonds of the methane molecule between the carbon and hydrogen. Each one of those bonds represents 2 electrons being shared in the outer valence shell. This is the molecular formula or the chemical formula of methane gas, CH4. Okay, CO2 would be the chemical formula for carbon dioxide. H2O would be the chemical formula for water. Okay, and what does it say? It says we have 1 molecule of carbon, or should say 1 atom of carbon and 4 atoms of hydrogen. H2O would be 2 atoms of hydrogen and 1 atom of oxygen. Glucose is C6H12O6. That's a sugar molecule, and we'll be getting into those real soon. Real quick primer on ionic bonds. And ionic bonds are a result of one atom losing an electron and another atom gaining electron. And as you can see, sodium on the left-hand side only has 1 valence electron, and chlorine on the right-hand side has 7 valence electrons. So it's much easier for sodium to lose an electron and therefore have 8 electrons in its outer shell. After it loses its 1 valence electrons, then that third shell disappears and we're only left with the 8 electrons in the second shell. Chlorine has 7 valence electrons. It's not going to lose all 7. It steals 1, and now it satisfies its octet rule. That's what it's called when there's 8 electrons in that outer shell. And everything's now good. But what has happened? Sodium has lost an electron. It has become positive because it's neutral to start with, loses 1 electron and becomes positive. Chlorine, which is neutral to start with, gains an electron. It now becomes negative. And we all know that positive and negatives kind of attract each other as opposites attract. We know that little cliche, and they do attract each other are attracted to each other in forming a ionic bond. And of course, sodium chloride is what we refer to as table salt. Table salt, this ionic compound in table salts, these are really strong bonds when they are dry. You throw these things in water and they break apart very rapidly, and we're going to talk some more about that, but that has to do with water's polar nature. It's basically a great solvent. It's going to go in and sort of tear apart the sodium and chlorides and kind of surround each one. And again, we'll talk more about that in class. Okay. The third type of bond that is extremely important, and I mean very, very, very important in terms of how our bodies operate and how the world sort of works, is a hydrogen bond. Hydrogen bonds are weak bonds, but in many molecules, like in DNA, we have a whole bunch of hydrogen bonds which help to hold the DNA molecule together. They also play a lot of role in the properties of water. And as you can see, they're kind of almost like an ionic bond. And what it is remember, the water molecule, the hydrogen side is slightly positive. And in this ammonia molecule down below, you see below the water molecule, that NH3 molecule, the nitrogen side is slightly negative. So it's kind of like a weak ionic bond because it's going to be a positive side attracted to a negative side. But again, weak but really, really important bonds, and we'll be spending some more time talking about those in the next lecture. All right, the last thing I want to talk about is our chemical reactions, and let's look at this chemical reaction we're seeing right here. And what we see is hydrogen, 2 molecules of hydrogen gas and 1 molecule of oxygen gas. Okay, and so we have 2H2 and 1O2, and those are the reactants. Okay, there's an abundance of those, and when they come together, they undergo a chemical transformation and get converted into water. Now, this usually happens when we burn fuel, things like gasoline, wood. When we burn those things, we release hydrogen molecules. They interact with oxygen molecules in the atmosphere, and they make water. And if you've ever seen water dripping out of the tailpipe of your car, That's a result of the combustion of those fossil fuels in your engine. A lot of water vapor comes out. I also want to point out sort of this conservation of mass. Let's count all the atoms. How many atoms do we have? Well, we got 4 atoms of hydrogen, and we have 2 atoms of oxygen on our reactant side. And then we look at our product side. What do we have? We got the same thing, 2 molecules of oxygen and 4 molecules of hydrogen. This is known as the law of conservation of mass. And again, one of those classic laws of physics, matter is neither created nor destroyed, just transferred or transformed in chemical reactions. So that the amount of matter in the universe has been constant ever since the universe's beginning. It's just being transformed into other things. And I will talk some more about this in class. Where did these things all come from in the first place? We will talk about that in class. Okay, I also wanted to point out that most chemical reactions can go both directions. So even though we're seeing the reactants being the hydrogen gas and the oxygen gas moving and this reaction going from left to right, it can also go from right to left. It all depends upon the situation and the energy that's being supplied and things of that nature. Well, that's it for today. Hope you enjoyed it. Thank you.